All right, let's begin. This is This is CS 4510, L13B, and this is the post-correspondence problem. Rice's theorem, and just a bunch more things, right? So first off, we just did a couple reductions. I've left the chart up there. Everything goes somewhere. Most problems we've proven to be undecidable are problems that are really referential in nature, in the sense that a Turing machine cannot decide things about Turing machines, right? Kind of makes sense that it's really self-referential in that way. There's two things we're going to prove. One, Rice's theorem. Basically, any question you can ask about Turing machines is undecidable. We're going to just generalize all proofs. Two, post-correspondence problem is a puzzle. It's a little kind of thing that basically proves not everything about, the only undecidable problems are not simply those that are about Turing machines, right? So Rice's theorem says that if P is a set of machine descriptions such that L of M has the property. The property could be, for example, being empty, containing the empty string, containing only even length strings, whatever the property is. If the property is semantic and non-trivial, we'll talk about these in a second, then P is undecidable. Okay? What do we mean by non-trivial? A property is non-trivial if not everything has it, right? Has or hasn't the property. Something has it, at least something has the property, at least something hasn't the property. Also notice that this is not machine word pairs or pairs of machines, just machines, okay? It is a question about not every machine. It cannot be the case, certainly if every machine has a property, then it's obviously decidable because you just have a machine that returns true. For example, that is a trivial property because every machine accepts 0 or more strings. So this is a trivial property. This is true for every machine, right? But in fact, non-trivial could be something like, does it accept any string? Right? One of these is trivial, one of them is non-trivial. Semantic is actually incredibly difficult to define, but in some sense it's about the language and not about the description. So it's not a question about the description of the machine, but about the language recognized by the machine. In fact, every machine must recognize some language, right? We are not asking about the code, we are asking about the behavior. So in some sense, determining behavior of a program is undecidable. There are trivial things you can determine about code. For example, does the Turing machine have 17 states? That's in fact a syntactic property, not a semantic one, because you can just look at the description of the Turing machine and you just count the states. Determining if a machine has 17 states is not semantic, so Rice's theorem doesn't apply. But it's about the language. So for example, is it empty? Or analogously, is this language recognizable by perhaps a different machine that has 17 states? That's unrecognizable. Is this the smallest machine that recognizes that language? Any problem you could ask, if it's about the behavior and not about the description of the machine, essentially a property semantic intuitively if it requires you to turn the machine on. You can never make such a definition full and precise though. For example, another one is, and in fact Alan Turing did this in his original paper. He did a very weak form of Rice's theorem and then it took like 40 years for someone to realize this. Does the machine use the third cell of the tape? That is a non-trivial property. Program analysis people who work in, for example, static analysis, they're concerned with For example, automated detection of memory leaks or things like this. So what they do is they write an algorithm that takes as input like billions of lines of code. They just test their algorithms on the Linux kernel source code, VLC source code, Firefox source code, things like this, and they see if there's an automated way to solve problems about the code. For example, memory leak issues by looking at the code. But everyone who works in program analysis is hyper aware of Rice's theorem because they cannot actually solve any of the problems. So they have to have realistic expectations about what their algorithm can do. So, for example, does the program have a memory leak? That's non-trivial. Why? Some programs do have memory leaks, some don't. It's semantic. It's about the behavior of the machine and not the description of the machine. So that's an example of something like this. Even virus testing, determining if a program is a virus, is undecidable. What we could define a virus as in a Turing machine sense is, does the machine ever make a copy of its code on the tape somewhere during any execution step? Semantic, non-trivial, undecidable. Virus detection is undecidable. Memory leak detection is undecidable. People who work in these areas know this, so they just kind of like hope for it. For example, let's say you're working in memory leak detection, and you run it on a Linux kernel source code. You have this interesting algorithm, and it finds 2 memory leaks, it says. Well, you have no idea if those are actually accurate. So you go manually inspect it, and you see actually one of them was a memory leak. That's kind of what happens in practice. You just kind of, there are still things you can try to do, but you know that you're up against such strong universal forces that you will never have a perfect algorithm for the problem you ask. That's all Rice's theorem really says. Let's prove it. The proof is incredibly simple. Let P be a non-trivial semantic property. We prove a reduction from the halting problem to P. The reduction is going to go as follows. It's going to take an input from the halting problem, and it's going to output a machine, let's say M prime. Now, we know some things already. First, without loss of generality, suppose the empty set hasn't the property. Yes. Why is that okay to assume without loss of generality? If we're talking about languages, every machine that accepts the empty set or accepts no strings, they're all either together in the property or all not in the property, okay? So if it is the case that the empty set does have, quote unquote, the property, for example, if the property was like, only contains even length strings vacuously, that would be true, I think, right? Because it contains no strings, so they're all even, because there's none of them. Just instead of doing the reduction to P, do the reduction to P complement. Then it hasn't the property, right? So without loss of generality, just suppose the empty set is something that doesn't have the property. Second, since P is non-trivial, some machine has the property. Call it M1, right? Some M1 is in P. Why is this okay? Because some machine hasn't, since it's non-trivial, some machine doesn't have the property, the empty set. Some machine does have the property. Let's just call it M1, okay? We code M prime as follows. M prime on input X is going to have M and W hard-coded. And as you know, it's going to simulate M on W, okay? Once it finishes that, it's going to simulate M1 on X and do whatever M1 does. So if M1 accepts, so will M prime. If M1 rejects, so will M prime. And if M1 is stuck in a loop, so will M prime. What this means here is that really M prime pretends to be M1 if and only if M accepts W. So it's going to pretend to have the property, whatever that happens to be, if and only if it accepts, right? Let's just do the if and only if. M comma W is in halt, implies M on W halts, which implies in the code of M prime, we're finished with this line of code, and we're going to here. So what do we know about the language, the behavior of M prime?
It does.
No, it does what?
It does what M1 does, as long as M accepts W.
Yeah, I mean, exactly. Yeah, it's going to be identical in every way to M1. Now, since M1 has the property, though, we know so does M prime. So, M prime has the property. Similarly, if M on input W is not in halt, that implies that M on W loops, which implies that the language of M prime is what? If M is stuck in a loop on input W, what will M prime do?
It'll never halt. It'll never accept.
Exactly. So what is the set of strings it accepts?
The empty set.
Exactly. Well, we know that the empty set doesn't have the property. The machines that accept no strings just by without our loss of generality don't have the property. So L of M prime doesn't have the property. Whatever that property is, having a memory leak, being a virus, using the third cell, whatever, right? Therefore, that's enough for us to prove that halt is reducible to P. Excuse me, halt reduces to P, yes, done. Therefore, P is undecided. QED. Okay. Questions on the Rice's theorem? Easy to apply it. It's actually a dangerous tool. Many students are asked to do a reduction, and instead of doing that, they'll be like, by Rice's theorem, this is undecidable. But it's too powerful. It's too dangerous. In some sense, it's a generalization of the three. We spent the whole lecture. We could have just began with this and just said, okay, ETM. Actually, that's the only one, because the other ones are not just machines. They're machine word pairs, right? Or machine-machine pairs. So in fact, this could immediately apply to ETM, but not really the others on a first glance. You would need a little bit more work. But it appears like anything is on, all the properties of Turing machines are undecidable. All of them. Fine. It is difficult also on this, what is a semantic property? You have to be careful. Because, for example, I claim using the third cell of the tape is semantic, but that's not really a question about what the languages are, right? So what you would have to do is modify this proof, for example, if you're proving the third cell is used, to make sure that you don't accidentally have the property when you're not supposed to. So, for example, when you simulate M on W, you need to do so in such a way that doesn't touch the third cell. Because if you use the third cell, you accidentally have the property. Something like this, right? The halting problem, ATM, EQTM, they're all undecidable. So what is decidable? I hate to erase the beautiful map. Suppose I ask a question of the following. Yes. Okay. So consider the following problems. We know we have the acceptance problem, we have the emptiness problem, we have the equality problem, and we have this other problem we haven't talked about called the all problem, which is like, does the machine accept all strings, right? Well, let's suppose we're considering decidability or undecidability, not of just Turing machines, but of the other devices we know, CFGs, and PDAs, and DFAs, NFAs, etc., right? The acceptance problem for Turing machine is undecidable. Agree? The equality problem for Turing machines is undecidable, right? Excuse me, the emptiness problem for Turing machines is undecidable, right? The equality problem of Turing machines is undecidable. Why is all TM undecidable? Yeah.
What's all TM again?
The language of the set of strings of the of machines that accept all strings. Does L of M equal sigma star? It's undecidable. Why? We get to apply Rice's theorem. For free, it's undecidable. Is it non-trivial? Some machine accepts all strings, some machine doesn't. Just write them down, okay, fine. Is it semantic? Yeah, it's about to be, okay. Undecidable, done. Suppose we're not working with something that's Turing complete. By the way, this is true also for all the other Turing complete models of computation. For example, unrestricted grammars. Does an unrestricted grammar ever produce a string? Does it produce all strings? Are two unrestricted grammars equal? Those are also undecidable problems because they simulate the Turing machines as well, right? What about the acceptance problems for DFAs? Is that decidable or undecidable? I give you a DFA and I give you a word. Is that decidable or not?
Yes.
Why?
Because they're finite, and you can always run it through.
Yeah, the algorithm just takes the DFA and the word and just runs the DFA and the word. Okay? The emptiness problem for DFAs, decidable or undecidable? This is an algorithms question, by the way. I give you a DFA, is it empty?
Feels like it should be decidable.
Yeah. Why?
It's trivial.
I mean, you can't apply Rice's theorem to things that are not Turing machines, but why is the empty, if I gave you a DFA, how can you determine if it doesn't accept a string, or it does accept a string, any string?
If you run it through the process we talked about earlier.
It's simpler than that because it's a DFA, but that actually would also work. But it's simpler than that. Just DFS. See if an accept state is reachable, right? If an accept state is reachable, it accepts something. And if no accept state is reachable, or in fact it has no accept states, then it can't accept anything. Decidable. Equality of DFAs. Decidable or undecidable?
Decidable.
Yeah, why? This is a difficult one, I'll tell you. Closure. You can prove two languages are equal if and only if their symmetric difference is 0, is empty. So you say, is the symmetric difference of the two DFAs empty? Yes. If not, no. Right? And in fact, wasn't there a homework problem that asked you to determine that the shortest string that two DFAs disagree on, if it exists, is of a certain length? So you finitely check so many strings, and that'll tell you if they're equal. I don't want to get into that too much more. In fact, there's so many ways you can answer that question. For example, it is true that DFAs can be uniquely minimized. So take two DFAs, run the minimization algorithm, and if they're equal, then they're the same. All DFA, decidable or undecidable? Does the machine reject a word? Does the DFA reject or not accept any string?
Decidable.
Yeah, why?
I want to say because you can run the parallel method.
Mm-hmm. That works, or DFS. If you DFS to a rejecting state, right? So DFAs have basically every problem about them you can ask is solvable by an algorithm. None of the problems you can ask about Turing machines appear to be solvable. What about CFGs? Is the acceptance problem for CFGs decidable? I give you CFG, I give you a word. Does the CFG produce the word? Or does the PDA accept the word? We actually did this one technically. A long time ago, we definitely forgot, but I'll tell you the answer. Chomsky normal form gives you a procedure to determine if a grammar accepts a word. You convert it to Chomsky normal form. You enumerate all possible 2n minus 1 productions. It's got to be in that list if it's there. If it's not in the list, it'll never produce it. So this is going to be decidable. The emptiness problem for CFGs. This is also tricky, but there's an algorithm for this. Basically, you look at the non-terminals and you mark any ones that have no non-terminals on the right. And then you try to like backtrack through the non-terminals and see if there's a way to get to the start from there. Kind of a complicated thing. I don't want to get super into it, but know that this is decidable. What about equality of CFGs?
Decidable.
I knew someone would say this because, and that's the point of this whole chart, I spent 5 minutes writing it. These two properties are undecidable. Determining if two context-free grammars are equivalent is undecidable. Determining if a context-free grammar accepts all strings is undecidable. That is interesting. You can determine if a context-free grammar produces anything. You cannot determine if a context-free grammar doesn't produce something. That is interesting. But it kind of makes sense because a context-free grammar is simply marking the good strings and just there's no indication about strings it doesn't produce, why it doesn't do so. But it just never produces certain strings. But it tells you when it does produce a string, but it doesn't tell you when it doesn't. So it's also interesting to note that it's kind of in between DFAs and Turing machines, as we know. And in fact, there are things that are kind of between DFAs and CFGs, and then we know context-sensitive grammars are between CFGs and Turing machines, right? So in fact, the more Turing complete you get, the more unsolvable questions start to arise. In the sense that when you're Turing complete, then basically everything is unsolvable. But if you have the more universal and general your model of computation, the less questions you can answer about it. They become self-referential. Now, the weaker they are, the more you can answer. The less strong they are, that you can't do those such things. Right? Questions on that? Okay. Let's talk about post-correspondence problem. Post-correspondence problem is simply a little puzzle. That's all it is. And it asks, given a set of dominoes, is there a match? I'll explain what that is. But all the undecidable problems we've talked about right now are about Turing machines. And so you would think, at a surface level, that the only thing that is undecidable is problems about programs. But we don't really care about that in a practical sense. And I care about like actual problems, not just property testing problems, right? So PCP is a language of tile sets, we'll call it P, such that P has a match. And what a match is that you have a set of dominoes, which are strings, and you have infinitely many copies of each domino. Is there a sequence of such dominoes that has the concatenation of the tops of the dominoes equal to the concatenations of the bottoms? So for example, let's suppose I had the following set of dominoes. B over CA, A over AB, CA over A, ABC over C. Okay? You have infinitely many copies of each. Give me a sequence of such dominoes such that the concatenations of the tops is equivalent to the concatenations of the bottom. Well, first problem. We need to choose a first domino. The first domino must begin with the same character on the top and the bottom. So we'll try this one. The second domino better begin with the B on the top. Let me write over here what's going on. We have AB on the top, and on the bottom we have ABCA. So we need a domino that begins with CA. Okay? So this now has CA, but it's added an A here. Okay? So we need something that begins with an A on the top to match this. So it could be this one or this one. Which one do I do? Let's do this one. So we put an A on the top, but it puts, but now we need something that begins with a, wait, is that right? A, B, C, A, B. Okay, yeah. Wait, no. Okay. Now we need something that begins not only with an A on the top, but an A, B, hopefully, right? Well, there we go. Notice that the concatenations at the top are equal to the concatenations at the bottom, even though they're partitioned in a different way. Right? But the concatenations at the top equal the concatenations at the bottom. Given a set of dominoes, we ask you, is there a match? Does there exist a sequence of the dominoes that you may concatenate together such that the top equals the bottom? Now notice that this is a set of dominoes that happens to have a match, but not every set of dominoes has a match. For example, this set certainly has no match. Explain to me why it has no match.
Since there's only one option on each domino, and they're not matched to each other, every time you try to even it out, you unbalance it with a B or an A.
Even simpler than that, there is no first domino because none of them start with the same symbol. PCP is undecidable. You cannot, given a set of dominoes, you cannot actually determine if the set of dominoes has a match or not. That's undecidable. But this is not a problem about Turing machines. This is not a meta problem. This is a puzzle, right? An unsolvable puzzle. And it's kind of a simple combinatorial thing that is used further in reductions, but it exists simply to be undecidable. It was defined, by the way, PCP stands for Post-Correspondence Problem. Emil Post is a tragedy of human history. He had one arm, and he was a logician, but he was basically beaten to the press by his entire career. He was kind of neurotic, and so he would often receive electroshock treatment. And he read Principia Mathematica, and observing that the way that symbols manipulate in a very syntactic form, he invented something that we would now call like an unrestricted grammar as a string rewriting system. So that was the first thing he did. He talked about a machine in parallel to Alan Turing, something called, we would now call a post machine, which is almost identical to a Turing machine, but it's a little different. Instead of cells, he called them squares, and the transition function is a little different. But he did not have a Church-Turing thesis. So although he came out with a very similar result, a diagonalizational argument, it was just nobody kind of cared. And that's kind of the important part of the philosophy there. And he didn't call his thing, computable. He had the term psychological fidelity, which is kind of strange. And so he didn't win any awards, and no one remembers him, and no one put him on any money for that reason. And because he was late to the press, he was not the first one to publish this result, and his work wasn't even as good. Then there was some other problem he solved, which was something called the word problem for groups. He showed such a problem was unsolvable. But a guy named Markov, you may have heard of him, showed the same problem to be unsolvable only months before. So basically, he was able to go toe-to-toe with many of the great computer scientists at these times, the logicians, but he was late on all of them. And for that reason, we don't really remember him for any significant contribution, except this problem. And it is really not any deficiency on his part, it's just pure luck. And during one of the electroshock treatments, I think he died. So his whole life is kind of not a second place kind of thing, right? Anyway, post-correspondence problem is undecidable. He constructed such a problem to be undecidable. We'll give a modern proof, and what we're going to do is simply give a reduction from the halting problem. What we've done previously is we have given reductions that take input machine word pairs and output machines. But here we want to output a set of dominoes. So in some sense, what we're going to do is create a set of dominoes that simulates a machine. A set of dominoes is a static object. It doesn't move. How can it simulate a machine? To some, a Turing machine is a static object. That doesn't move. So how can a Turing machine, there's no real notion of being dynamic. So that's kind of what the proof relies on, is that the match exists only if the machine halts. And the quote-unquote dominoes are going to simulate the machine. And we're going to construct the dominoes essentially to force such a simulation. And the match will only exist if the machine halts. Otherwise, there'd be an infinite match, which is not a real match, right? So that's kind of what's going to happen. First, notice that we can kind of do quote-unquote programming with dominoes. In the sense that if there is a match, we can force something about them. So for example, if we force the start tile to be this, sorry, if we add this tile, there is only one tile that starts with the same symbol. So if there is a match, it is forced to be this one, right? Now, because we begin with a deficiency on the bottom, we can now force the next choice of tile. Has to be that one, right? Wait, hold on. Ah, there we go. Okay, yes. We can now force the next choice of tile. It has to be that one. It's the only one with a B on the bottom. Excuse me, an A on the bottom. We can now force the next choice of tile. Is this right?
Yes.
It has to be this one. So, although there is no algorithm that necessarily chooses things in order, you do not get to assume, for example, the algorithm chooses things in order. You can construct the dominoes in such a way that if it were to choose them in order, it must choose this one first, and then that may force the next choice to be exactly this one, which may force the next choice to be exactly this one, which may force the next choice to be exactly this one. Okay. The string that we will produce by the dominoes will in fact be what's called a computation history of the Turing machine. So suppose, for example, we have a bit flip machine. So we move left. A computation history of such a machine is a sequence of configurations. So we simply encode those sequence of configurations into a string, and we're going to make sure the domino produces that string. So for example, this machine on a string, let's say 1, 0, would be the following. Q0, 1, 0, right? The next configuration would be what?
0Q0.
Yes. And then the next one?
1Q. Or sorry, 0.
Yeah, let's just say there's a blank there. And then 0, 1, no, sorry, we're gonna move left, right? So we're gonna say QH, 1 blank, okay? This is called the computation history. It is a string of certain syntactical properties, right? Notice, chief among them, it exists if and only if the machine halts. A grammatically correct, we'll forget the term grammatical, a correct computation history is a string that exists if and only if the machine halts. in the sense that it corresponds to the transition function of the Turing machine. So we're going to create a set of dominoes such that the match will be the computation history. Only the computation history and no other string on accident. Therefore, the string match only exists if the computation history exists. The computation history exists only if the machine halts. That's going to be the idea of the proof. Now, as we proceed with quote-unquote choosing dominoes and forcing decisions, we are going to force whatever algorithm is choosing dominoes, we will trick it to computing a Turing machine for us by repeatedly applying delta. We will begin with a domino that looks like something like this. Okay? And what that is going to be the initial configuration. By having a deficiency on the top, the next few dominoes are forced to be chosen in such a way. But as it chooses those dominoes to put C0 here, we will make sure that the tops of the dominoes allow it to compute a match for C0 to C0, but we'll ensure the bottoms of the dominoes then force the machine to write down C1. Then as it now has to match this deficiency of C1, it's going to put C2. C2 goes here, it's going to force it to write C3. Okay? Yes?
So we have full control over the dominoes.
You'll have to actually see, yes, exactly. This is the output of our reduction. And we'll actually give the set of dominoes, but we're just kind of explaining high level why they work. Now we only want the match to exist if the machine halts. So what we will create is an end cap piece that's kind of shaped like this, right? And that'll be the only piece that'll work. It'll be like hash, hash, QH, something like this. And that's going to be only correctly be able to be matched in if and only if the machine halts, right? And that'll only happen if the configuration on the bottom here was a halting one. So that's kind of how we'll ensure that there's a match. Right. Let's get into the kind of the programming. So first, and again, we want to take a machine and a word and write down a set of dominoes. So what the reduction is going to first do is write down the following domino. That hopefully will be our start. We'll have to make sure later on that we're careful to not accidentally include other dominoes that don't begin with the same symbol, so this is forced to be the start. We'll hope that this is the only starting one, okay? Second thing we need to do is define, in the same way we simulated a Turing machine on an unrestricted grammar, we're going to simulate, quote unquote, the Turing machine here on the set of dominoes. So we need dominoes for left and right moves. Suppose we have a right move of the form, we read A, we write B, and we move right. Let's say we go from QI to QJ. Observe the way that sequential configurations are really like rewriting small portions of the previous configurations, right? So if we had in a configuration QIA, the next configuration ought to be BQJ if we're moving right. So we will add the domino QIA BQJ. As it is forced to match the top, it's going to choose dominoes that have a QI on the top. We're going to make sure BQJ is on the bottom. So as it's forced to choose dominoes to match the top, it's forced to write the next configuration on the bottom. And this is how it does this small part of the configurations, right? Do we agree that this simulates the right move?
So that assumes that there's already an A there from the last one?
You can only apply it, for example, we'll make sure that there's many little details in this. We're just doing the high level part for now, and we'll polish those up as we get into it. The problem now is the left move. Read A, write a B, and move left. And this is for any AB. AB is blank, 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 whatever, right? Now, the way you would do this one is that if you're at QIA and you move, instead of moving right, you move left. So this is going to be a B, but then QJ is going to be over here, and this is going to be something, right? So whatever that something is, we need to make sure that it's there. So for example, if this was X, then this is now X, right? So what we're going to do is put it for all possible symbols that could appear on the tape. So we have AQIA to QJAB, BQIA, QJBB, and blank QIA, QJ blank B, right? This is simply coping for the fact that our configuration, way we've encoded the string is imbalanced. Okay, that's basically the entire proof, but now we need a bunch of little helper pieces, okay? So, right, the helper pieces are going to help us copy the rest of the tape. So we're going to have the following tiles: A over A, B over B, and blank over blank. There is an immediate problem we have induced by adding these tiles, though. These will copy the portions of the tape not near the head. But by adding these tiles, we've done something horrible, actually. What is it? Yes?
There's no cues on there, so
Well, notice that the only portion of the tape that would be modified is near the head. But the tape could have 1,000 cells on it already written to from previous things, and then we only want to change from sequential configuration this to this, the local portion. But we still want to copy the rest of the tape over. These are for copying. What I mean is the problem is in the reduction now. We've broken the correctness because any tile set with those dominoes already has a match. Just choose AA. That's bad. We'll have to come back and fix that. But for now, that's what we're going to do. Okay? Then we need to add tiles that help us transition between configurations, and also those that can give us additional space if we need it. And so this one will be on the bottom. Right. If we need an extra blank for whatever reason, we can insert such a tile. Okay? Now, the problem is that there are multiple accepting configurations of a Turing machine, right? So how do we get this end cap on here for the, what if it halts with a bunch of garbage left on the tape? I don't want that. So what we could do two things. One, we could fix this in the simulation with the tiles, or we just declare, before we perform the reduction, first we make sure we modify the Turing machine so that it cleans up its tape before accepting or halting. That's possible, right? You just replace the halt state with a cleanup subroutine, and then it halts, right? That's not improbable to do. So we do that, and then we add our cap tile, which is going to be this one, QH. So if there's no tape, that's the only thing there, right? Notice that's the only one with a longer top than a bottom. So this is the only one with a longer bottom than the top. We will start with this one. These are going to be applied uniformly throughout the computation, and then that's the only one that's allowed to finish the deficiency and end the cap. Okay? These are all the tiles that are necessary for the computation. Okay, that's it. Now we have that problem again where we've added these at the beginning. We can describe how to fix that. But do we agree that this set of dominoes, if you forget that issue, has a match if and only if the machine halts? Yes?
So with the copy ones, AA, BB, I know you said that we'll come back to it, so this might be for later, but how would you even use those if you're always deficient on the top?
Well, you need to copy the rest. So C0, C1, C2 here, of course, are a string, so they're multiple things with hashes in between them. right? So what you need to do is not just copy the portion of the tape near the head, which are these, but copy the rest of the tape over. So when you do the next hash, then you get your, you can do the next move and so on,
Because
right?
the configuration is the whole tape.
Exactly, exactly. That's what we mean by copy, is that just copies the rest of the configuration for us, with the small modification that is the left and right moves. Okay. Let's fix the last little issue. So what we're going to do is modify the tiles in the following way to force the first tile to be the first one, the last tile to be the last one. Suppose we have a set of tiles as follows. We want TS and BS to be the start tile. Right now it's not special, but we want to force, if there is a match, for it to be the start tile. Let's suppose then we have T1, B1 to TK, BK. And then we also have a tile we want to force to be the end. We'll call it TE, BE, okay? We will modify these to start with the same special symbol. So what we're going to do is say that if W is equal to W1 to Wn, we say dot W is equal to dot W1 dot Wn. W dot is going to be W1 dot Wn dot, and then dot W dot is going to be W1, dot W1 dot Wn dot, okay? So we define these three operations on strings to be append a dot before every character, or after every character, or both, okay? Then all we do is transform this set of tiles into the following. Dot TS over dot BS, and then the dot will go on the bottom. For the others, we will transform these into dot TI over BI dot. Notice by doing so, we have now prevented any of these intermediary tiles from beginning with the same symbol. So therefore, none of these can now start, because none of them appear with the dot. And the last tile will be dot top E over, dot over BE dot. The computation now takes twice as long because we've inserted a bunch of dots, but doesn't matter, it's still correct. The only tile that's allowed to start with the same symbol is now this one. The only tile that's allowed to end with the same symbol is this one. None of these can begin the computation. Done. This is sufficient for us to prove a correct reduction from the halting problem to PCP. So therefore, post-correspondence problem is undecidable. Done. A simple combinatorial thing that has nothing to do with machines. There's no code written down. We now have an unsolvable game. Questions on post-correspondence problem? If you recall from the theory of NP completeness, when you do a reduction, you now have a new problem. And then you can reduce that from that problem. And it makes some proof simpler, right? From independent set, you can go to vertex cover faster than you could if you try to do the cumbersome reduction all over again from SAT. You can compose reductions, right? So in fact, we can use PCP as something to reduce from now, and other things. I will give a reduction from PCP to this overlapping problem for context-free grammars, where overlap CFG is defined to be pairs of grammars, CFGs specifically, such that they share at least one string, right? L of G1 intersect L of G2 is not the empty set. Now, why am I choosing this language instead of EQ-CFG or all CFG to demonstrate? Simply because the proof is simple. Okay, that's the only reason I'm going to do it. Proof is actually trivial from PCP. Here's how we're going to do it. Given a set of dominoes in here, we want our reduction to take a set of dominoes and output 2 grammars. And in fact, what we're going to do is construct the 2 grammars to share the string, which is the match. So one grammar is going to produce the tops, one grammar is going to produce the bottoms. Okay. The other grammar is going to be the same. We'll call this S1 for G1. And S2 is going to produce B1 S2 B2 BK S2 or B1 BK, right? Where the tile set is going to is initialized to be T1 over B1 to TK over BK, right? So you take a grammar to produce the tops, concatenations of the tops, in fact, and concatenations of the bottoms. Actually, these are even both regular grammars, if you think about it. But now, there's a bug, though. There's a problem. These 2 grammars will produce the same string that happens to be the match. But it doesn't preserve the correctness because it doesn't enforce that let's suppose that there's a match. It must be the case that a set of tiles is chosen in an order. We want the set of productions to be chosen in exactly the same order. But the problem is that these 2 could match in a way we don't want them to by this choosing them in a different order than this one. And we want to force, when a top is chosen, a bottom must be chosen. So we want the sequence of productions to be the same and not just the string produced. How do we fix this? We're just going to expand the alphabets to include dummy characters, call it C1 to CK. And we'll append to each rule to force us to choose those in a specific order. So this is going to be T1 S1 C1 ... TK S1 CK, and then all of these are going to be T1 C1 TK CK. This is going to be B1 S2 C1 ... BK S2 CK, B1 C1 to BK CK, where C1 through CK are not strings, but single symbols from the alphabet, right? Now, convince yourself that these 2 grammars have a match if and only if the set of dominoes had a match, right? If the set of dominoes has a match, and I'm not going to write this down, but I'm going to just say it out loud. If the set of dominoes has a match, there's a sequence of dominoes that is the match. You can choose a certain number of those. Take the corresponding sequence of productions for both grammars. Therefore, T1 is going to be, let's say T1, this one is chosen, then this one is chosen, then this one is chosen, then this one is chosen. Notice then that the symbols after this are all going to be the same because they're going to be the same sequence of moves. So it's going to be, for example, C3, C2, C3, C1. Then the strings that come before are going to be concatenations of the tops and the bottoms, which are then just going to correspond exactly to the match.
I like it.
So you can determine if 2 grammars overlap if and only if a set of dominoes is a match. Right. Questions on that? Yes?
So in this case, instead of creating the dominoes, we created the grammar that represents the dominoes?
Exactly, exactly. Reduce from halt to PCP, but once we have a simple problem, which is highly combinatorial, you can actually prove many, many things. I have time and one more thing I can show you. The first thing I'll show you is, as soon as this works. Okay, so what other problems are unsolvable? There's something called Hilbert's 10th problem, which claims Hilbert had many unsolved problems, and many of them ended up being undecidable. He didn't like this. One of the such problems was called Hilbert's 10th problems, which claimed that the set of, if a Diophantine equation is a polynomial, over integer coefficients, okay? So, for example, a to the n plus b to the n plus c to the n, if n is fixed, and only if n is fixed, is a polynomial, okay? People tried to prove it's solvable. It's actually unsolvable. So what happened is three guys, Martin Davis, Hilary Putnam, and Julia Robinson proved that the set of recursively enumerable languages is exponential Diophantine. They were unable to prove it's Diophantine. Something like 20, 30 years pass, a young guy named Matyasevich in the Soviet Union is working on this problem independently, and he proves that Fibonacci numbers have the property that they seek. So he completes the last piece of the puzzle. And among that, he proves that given an arbitrary Diophantine equation, which is something that looks like this, it's got integer coefficients, and it has, the variables are only allowed to take on natural numbers, or even integers, doesn't really matter. Such a problem is undecidable to determine, does this Diophantine equation have a solution at all? So among the unsolvability of that, we get many interesting things, because for each algorithm corresponds a Diophantine equation. This specifically is called the Jones-Wada-Wiens something polynomial. Let's get this right. Jones-Sato-Wada-Wiens polynomial. And among it is the fact that the positive solutions to this polynomial are the prime numbers. So this is a formula, in some sense, for the prime numbers. Now, it's been modified. What they kind of did, a way to think about it, is they took the Turing machine, not exactly, they took something else, but they took the Turing machine and they performed the reduction to the Diophantine equations, the same way if you actually had a tile set, you could actually give the two grammars. Or if you actually had a machine, you could actually give the tile set. Literally take the machine that prints only prime numbers. It does some division, a little bit of checking, mod, whatever, it's fine enough. Maybe 200 states, who cares? Convert it to an equation, and then apply equational techniques to reduce it. Now this formula is incredibly aesthetically pleasing because it has exactly 26 variables. And that is exactly the number of letters in the alphabet. You can reduce it, but then it gets uglier, or you can make it simpler, but then you need to say like x1, and that's kind of ugly. So this is an aesthetically pleasing formula. That happens to be the solution to the prime numbers. And that's crazy that we have a formula for prime numbers like this. Kind of. So I'll tell you a story. Yuri Matyasevich is going on his world tour after solving Hilbert's 10th problem, and there's a conference in the Soviet Union held in honor of an ancient mathematician at this point. He's retiring, and I think his name was Linux, and he's like being pushed around in a wheelchair, and someone explains to him the result. He says, Matyasevich has found a Diophantine equation whose only positive solutions are prime numbers. And Linux says something like, great, we're going to learn many things about prime numbers. And then he says, actually no, the result is far more general. Matyasevich has found a polynomial whose positive solutions are exactly and only those of every recognizable language. And he says, so we'll learn nothing about the prime numbers. So in fact, there's nothing interesting about this in a primality sense because there exists such an equation for everything there exists an algorithm for. So there's no more interest in such an equation than there is interest that there is an algorithm. That doesn't tell us anything. In fact, this can't even help you determine prime numbers efficiently. First of all, it's factored. If it's prime, we know something that k plus 2 must already be 1 or a prime. This whole thing must be 1, and this must be prime, or this must be -1, right? So it's already factored for us. That's problematic. The second thing is, finding a root of this polynomial that's positive is very difficult. If you try to strat test it, you just throw numbers into it, plug and chug A through Z randomly. I could not find a positive solution. I found millions of negative solutions to a polynomial. I could not find a single positive one. And then I did a little bit more research and I found that there was a master's thesis to find a single positive solution to this specific polynomial. It was worthy of an entire master's thesis to computationally find a positive solution to an equation like this. But it was, and which prime number you're gonna guess? It's gonna be 2. So we know 2 is prime because it's a positive solution to such a equation. That doesn't really help us. That's Hilbert's 10th problem. Okay, I'm over time. I'm gonna keep going. Sorry. Wait, hold on. Nope. Oh wait, hold on. Do you guys know what Baba is you is? What? We heard Baba is you. Baba is you is this interesting little puzzle game. It's in every itch.io bundle. It's in every, have you guys seen this before? Baba is you. Essentially, it's a very simple game where, I'll just play some of it for you. So let's do level 1. Essentially, the rules of the game are written within the game. Well, let me turn that's off, okay. So here's Baba, I move left and right, and there are these other blocks, I'm moving up, it's stopping me. And that's, the reason it does so is because there's a rule there that says wall is stop. So, I can modify the rules of the game in the game by doing this. I've now destroyed that rule, and look, I can move outside the walls, right? What do you guys think will happen if I destroy this Baba is you rule?
You die.
Yeah. Okay, undo. Okay, now, normally what you're supposed to do here is say flag is win, and then you touch the flag, you win. But you can actually do some more interesting things. For example, you can create any rules that you want. Let's say wall is you, okay?
Huh.
Let's create the flag is win rule. And now we just go touch the flag, okay? The reason I'm showing you Baba is you is because, in fact, Baba is you is undecidable. Given an arbitrary Baba is you level, it is unsolvable to determine whether or not it has a solution. That's not the one. So there was, oh no, there was this paper, 2019 I think, that proved this. It was kind of cute. And what they did is did a reduction basically from PCP. So here's a high-level reduction. You restrict the level in such a way that given a PCP instance, you create a Baba is you level. The only valid moves that you allow Baba to do by the reduction are push these little buttons here. So there's a chicken, a bat, and I don't know, a tree, an acorn. And the sequence of the level is programmed in such a way, according to the valid rules of Baba is you, such that the sequence that Baba pushes those in will produce tiles on the bottom. And the level is only solvable if the tiles have a match. So for example, he's going to push that one. There's this dog gadget here that serves as a clock, and it removes control from Baba until the tiles have moved all the way to the end. And that's just so, so he pushes that one, he pushes that tile. It's actually not directly from PCP, it's from a bounded version of PCP, complement, which is the same thing. The water basically has to collapse the lava, right? So he's going to push one more tile. And notice that those are complements of each other. Now he's going to push the go button. Right? Pushes the go button and he wins, right? So a Baba is you level is undecidable because it can encode an arbitrary PCP instance such that the level is beatable if and only if a PCP instance has a match. But since it's undecidable to determine if a PCP instance has a match, it's undecidable to determine if Baba is you, given an arbitrary Baba is you level, if it's solvable. If someone says, I have an auto solver for every Baba is you level, you say, great, you give them an instance of PCP and you say, fine, you can trick them into finding a match for you, right? Now, this is not the full reduction. There's lots of little gadgets, so we could do, there's all these other rules that are necessary in little catches and if statements and little cases that are there to ensure that it actually works as desired, and there's a little bit more complexity involved. it's a bit cumbersome. But the important thing is that it works, right? The dog clock is there, all these other rules are there. Sometimes the idea of the reduction is simpler than the actual reduction. Anyway, there are many unsolvable games, undecidable games. Braid, I think, is undecidable. Battleship can be undecidable. There's many such combinatorial objects that are, in an unbounded sense, undecidable. You may know that there are many NP-complete puzzles, right? A game is the difference between undecidability and NP-completeness really is that they are over an unbounded domain. That's what really makes them totally unsolvable. There are many combinatorial problems that are unsolvable. Given a set of tiles, can you tile the plane in such a way? Can you create certain objects? N-dimensional folding of knots. Given a set of matrices, does a product of them equal the zero matrix? There are so many undecidable problems that appear naturally at higher levels, but they kind of come through PCP, which comes through a self-referential argument through the halting problem. So very disconnected things from the halting problem. Do we know that all these problems are unsolvable? All right. Questions on that? Okay, goodbye.